We have gathered today for our second session on classification. So it is, and the top of the screen says classification. The last time we did classification, and I mentioned that classification is a process. It's think of it as a black box, right? Or not a black box, but a magic box. You give it some features, and out comes a prediction, which is to identify a type. For example, if you give the height of an animal, the weight of an animal, the color, and some other features about an animal, and you ask the magic box, what animal is it? And it might say cow, duck, horse, and so forth. So that is classification. More realistically, you may classification examples of classification is you get a credit card transaction. Is that transaction fraudulent? Right? You need to decide as a credit card company, you need to decide quickly because the merchant and the customer both are waiting. The payment and transaction is in progress. You need to quickly determine that. So that you use models to do the prediction. So that is an example of using a classifier. Here you're trying to identify valid transaction or potentially fraudulent transaction, isn't it? Another would be like you are looking at the biomedical markers, some blood test results and so forth, some biomedical markers. You're trying to determine whether the person uh, that these markers belong to, these lab results belong to, does she or does she not have breast cancer? This is a lab example, by the way. We will do that example in this workshop. Hopefully, the week after Diwali, that is the example I'll use to explain classifiers. And it's very instructive that machine learning can do that. Uh, the question is a binary question, it's still a classification problem. Identify, does this, when you look at this picture of the tissue or the X-ray, does this person have breast cancer or not? Does this person have heart disease? Like, suppose you look at the MRI data. Does this person have clogging in the arteries? Does the person have heart disease or not? And today, the state of the art in machine learning, in AI, has reached a level, surprisingly, and this has just happened in the last 2 years, that we are doing in many ways better than any experienced physician will do. So what happens is, in some of these tests, a classification algorithm outperforms the average physician, the average doctor, and it matches the top-notch doctors in its performance, which is a very remarkable thing. We used to think that medical diagnosis, the ability to tell whether somebody has a disease or not, it is the domain that purely belongs to human beings, and not just human beings, to a very elite group of highly trained individuals, medically trained, who have gone through 10, 15 years of medical training, who can tell correctly whether a person has something or not. And we are realizing that machines can beat us at that. So one recent breakthrough that was there in this space was that I don't know if it is done in India yet or not, but here you look at a map of the eye. When you go for an eye checkup in the US, you go for the annual eye checkup. So then your ophthalmologist, the eye doctor, he will take a picture of your eye, the corona. It's called the I think it's called the optodome. That's the word. So it's a nice big round circle. Some of you may have seen that picture of yours. It was only to decide if they have eye disease. It has been done for enough number of years in the US that there is massive amounts of data across large number of patients. So one person who got an interesting idea, he said, what else is there in this picture that we don't know, that we weren't looking for? And to everybody's great surprise, it turns out that if you have diabetes, and how strong your diabetes is written in your optodome. How, whether or not you have heart disease is very accurately written in your optodome. And human beings can't see it where it is written. But an AI can read it somehow and tell that this person has heart disease or this person has diabetes and a whole host of other diseases, I believe something to do with kidney and so forth. So in our eyes are written the signatures of all that is happening in our body. It's a very recent breakthrough, as in the last couple of years it has happened. And it has everybody surprised. It is a classification algorithm. That's the power of it. So when I'm explaining it to you, I'm explaining it with cats and dogs and horses and cows. But I just thought I'll bring in the reality, that the reality is that, but the algorithm is the same process, same theory, same everything that I'm teaching. You just applied it to a different problem. This is also true for lung X-rays. It turns out that lung X-rays are another big map to our body. In our lungs, a lot of things are written in the X-rays of that. All sorts of respiratory illness can be seen there, and it is beginning to see things that very few people are able to see actually when they look at a lung X-ray or not X-ray, MRI data of the lungs and so forth. So that is the new frontier for classification. Now the question that arises and that we asked last time is, how good is this algorithm? How do you know? You make a magic box, a classification, a classifier box. How do you know that this is a good classifier box? So the way you do that is you look at something called the confusion matrix. The confusion matrix tells you that of the cows, let's see, if you look at this yellow thing here, let me highlight it again. You look at this, let me make it fatter. You look at this big circle that I made. This is the confusion matrix. And the truth or the performance of every metric of performance about a classifier is derived from this. So for example, here is a cow. How many cows did you get right? 40 of them. You caught the cows as cows, but then you thought 10 of the cows are 10 of the cows you marked it as ducks. Right. So obviously, you can imagine that you would never do that. But one easy way to think of artificial intelligence, and I always give people this intuition, think of artificial intelligence as a 2-year-old child. The two-year-old child is pretty bright, but there's a lot of learning yet to be done. And I have found it useful. I don't know whether the intelligence maps to that. I don't think so. But I found it easy to reason about artificial intelligence or machine learning or data science by always thinking that these magic boxes, that they are somewhat like a 2-year-old child, and you're training them, you're teaching them, and then they're still making mistakes. So you can imagine that a 2-year-old child can confuse a cow for a duck and a duck for a cow. And so you look at the accuracy measure, how many you got right. Right? So this is it. Accuracy is how many you got right versus how many you did not get right. Now I said that accuracy, while it is a rough measure, it shouldn't be the only measure. If the data is highly skewed, accuracy is actually meaningless. What you really care for a rare disease, let's say that you're looking at cancer. If you are looking at, let's say that you want to do early detection of breast cancer, which is important in cancer, even if you have the slightest hint that things are wrong, you should be sent for further testing. You want to catch it as early as possible because a cancer caught early is just like any other disease. It is curable, completely curable. A cancer caught late kills people. Right? So as the cancer progresses, your chances of survival keep going down. So it is important to catch it early in the annual checkups. Okay? Which is one reason, of course, we do annual checkups. We want to make sure that nothing is just growing for years. You catch it as early as possible. So suppose cancer incidence is 1 in 1,000. You realize that giving an accuracy of 99% in an algorithm is meaningless. The most important metric is whether you caught the guy who has cancer. Right? Now, it's hard to pinpoint that guy because it's a needle in a haystack. To pinpoint the person who has that, this instrument can be a little bit hypersensitive. So even if a person is healthy, but something looks odd, in the, let's say, the X-ray or something, you want that in the early screening, it should just mark you as positive. It should err on the side of caution, right? And so you are willing to tolerate a lot of false positives, but not false negative. If you miss, yeah, false negative. A false negative means the person had cancer and you missed it. You said he's okay, because that can be catastrophic, isn't it? The person will now go home happily. 1 year later, will come back. By the time the cancer would have spread. Right. On the other hand, what is the worst that will happen in an early screening? If you, a totally healthy person, you give a false positive reading and say you have cancer. Well, the worst that will happen is that person will become terribly sad, go home, write his well, right? And there'll be a lot of crying and sadness and all of that. And then the doctor will, maybe 2 weeks later, do more tests, and the new test will come back and say, well, actually, you don't have cancer, right? So you may just have 2 weeks of high drama in the house, but it is a far better, it's a far safer thing that the worst thing that happened is drama in the house rather than missed cancer, right? So that is the value of early screening tests. They should err on the side of not missing anything. So the word that you use is you need high recall, and I'll explain the concept to you guys in a little bit. Then on the other hand, the final test, so you mark somebody as potentially having cancer. Now, let's say that 9 out of 10 people that you marked as potentially having cancer, they don't have cancer. That's all right. You just need a second test whose purpose is not to avoid missing anybody, but its goal is entirely different. It is to not have false, uh, what is that? False positives. You can have false negative for the final test because you know that a previous test has already been careful about that. You now want to make sure that if you declare somebody to have cancer, that person better really have cancer, right? Otherwise, you shouldn't declare the person to have cancer because after that comes rather a regimen of rather unpleasant therapies, you know, chemotherapy and radiation and so forth, and that are fairly invasive on the human body. So only cancerous patients should go there. So that is it. You know, you have to balance. What are you aiming for? Low false negatives or low false positives, right? You have to set your goal first and then pursue your goal accordingly. Right? So that is the thing that we were talking about last time. I talked a little bit about the receiver operator characteristic curve, ROC curve, and the basic idea was that you want to, you have a sliding scale, how sensitive you want to make your equipment. If you make your equipment too sensitive, you'll start having a lot of false positive. You want your equipment to be at a situation where most of the cases are true positive. You catch your true positive rate is very high and your false positive rate is low, isn't it? Ideally, you want such an instrument. It catches, if it declares somebody to have cancer, that person probably has cancer, right? You don't have false positives. And the converse is also true. You don't want false negatives. So that is your receiver operator characteristic curve. Now, most people don't remember it by its full name. They just call it the ROC curve. Are we together? And then what you look at is the area under the ROC curve, which is that how much space you have under the green line. The more the area, the better. And the maximum value that you can have, so the AU ROC curve takes values between 0 and 1. So the closer it is to 1, the better is your algorithm. Right? So these are the ways that you understand a classifier. Now you say, well, that classifier is a very interesting magic box. How do people build it? Like what approaches have people taken to build that magic box? So it turns out that the literature, the field of machine learning is rich. There are literally, I mean, it is hard to count how many algorithms there are. very rich literature. Uh, and I personally, after being in this for years, decades, I still don't know or encounter very often some new classifier that has existed for 10, 15 years, maybe 20 years. I was just not aware of it. Okay? So it's a vast world out here that you do. But what we will do today is we will deal with uh, something like linear regression, very commonly used. It's called logistic regression. Logistic regression is not a regression algorithm despite its name. It's a classifier. It's a classification algorithm. So we will understand that in depth. After that, there are many algorithms. They all behave the same way. You can think of them as a magic box. Uh, I'll just give logistic regression as an example of the beauty and the power of how these magic boxes work. And to understand that should hopefully be enough to give you a sense that other magic boxes also use very clever tricks, very clever ideas on how to catch or how to distinguish the cow from the duck and so forth. Right? So remember that the logistic regression is just one of the classifiers. It's a rich literature. So when we do the lab, we'll do a lot of other classifiers. You won't understand, I mean, you don't need to know the theory of it in the beginning, but you just need to know that they behave and work in the same way. They just have different performances. For example, for many situations, a random forest may do much better. For some situations, support vector machines may do much better, and so forth. So that is it. But which algorithm will work best, you never can tell. These days, neural networks are very much in vogue. A lot of people swear by deep neural networks, right? Or deep learning is the marketing buzzword is. A more appropriate word actually should be perhaps representation learning. There's a class of algorithms that deal with that, and quite often used these days. And obviously, it just so happens that I teach that 2 days a week, Monday, Wednesday. So that class is going on. You'll see some videos of mine.